Hello, everyone. We are the test engineering group for airfoil performance and geometry mapping. I'd like to start this presentation by giving a quick background of our project. So, the main objectives of this project was to select different airfoils with different geometries and measure lift and drag acting on them at varying speeds and angles of attack in order to determine the best overall aerodynamic performance. And the second part of this project included performing an accurate mapping on each airfoil selected to potentially be used in future labs for at Clarkson. The significance of this project is to increase lift and to reduce drag. Doing so, it would result in a better efficiency of the airfoil. The quick question in this project was, what is the best airfoil geometry that will give us the best lift to drag ratio and the best CL over alpha curve?
The experimental plan for this project involved testing three different airfoils at both low speeds between 2 to 4 Hz and high speeds 5 to 6 Hz at varying angles of attack ranging from -2 degrees to 14 degrees, changing the angle of attack in increments of 2 degrees. This process was repeated for both lift and drag measurements for all airfoils. The procedure for the aerodynamic performance of the airfoils involves first calibrating both the lift and drag ports of the wind tunnel using a combination of pulleys and weights which were measured prior to starting. We then properly wire the outputs for the drag sensors to the computer using the channel board and the force sensors attached to the wind tunnel. We then record the pressure inside the wind tunnel at zero velocity, record the pressure inside the wind tunnel at experimental velocities of 2 Hz, 3 Hz, 4 Hz, 5 Hz, and 6 Hz. We use these results later to determine the true wind speed. Next, we calibrate the input ports using LabVIEW and adjusting the sensitivity on the channel board using a flathead screwdriver. We want the number to be as close to zero at the starting point. At this point, we then record the data for drag at the multiple speeds and angles of attack. After all data is collected for the drag, we then repeat this process, but we wire everything for lift instead of drag. The procedure for geometry mapping was performed after the aerodynamic testing and involved going to the makerspace and using Peel 3D to scan the airfoils to make a rendered image. We then import that image into Fusion 360. There, we correct the geometry, and then once the geometry is corrected, we save the STL files, import those coordinates into MATLAB, where we then plot the coordinates to create the airfoil shape and determine equations to describe that shape.
The equipment used for this project was a signal input channel board, which was wired in a Wheatstone bridge, a wind tunnel, which allowed us to change the wind speed and the angle of attack, and a manometer, which allowed us to read the pressure in inches of water of the air. These are images of the three different airfoils that we use for our tests and their cross sections that we got from our scans. For safety risk assessment, we identified the risks of using the wind tunnel. Potential hazards are the rotating fan blades, the high air speeds, the high voltage components, and loud noises generated from the wind tunnel. Another risk is if the airfoil broke or a part broke in the wind tunnel, which would then get lodged into the blades, damaging the wind tunnel. To mitigate our risks, we used safety glasses at all times and used ear protection. We also debriefed with Professor Hoover before using the wind tunnel on how to use it.
So moving into our results, the lift drag ratio on all the airfoils. This data that you're seeing is for a motor velocity of 6 hertz, which represents to um, approximately 112 miles per hour. So this is just one section of all of our data. Our spreadsheet contains many other data points, but for simplicity, we didn't include those data points in this presentation. But based on the average L over D ratio for all the airfoils, we determined that airfoil 2 has the best L over D ratio at 3.92. Moving into our results for the lift coefficient versus the angle of attack, these plots are for a Reynolds number of a little over 400,000. And based on these plots, it was determined that Airflow 2 has the best overall curve because it shows the greater L over D max value of a little over zero point 0.3. Going into the results for the second part of this project, which was the airflow geometry mapping, we performed mapping on all the airfoils analyzed in this project. These airfoils were plotted using MATLAB, as you can see on the left, and then on the right, you can see the upper and lower surfaces equations for all the airfoils. After carefully conducting the procedure for this project, our group would like to conclude that Airfoil 2 presents the best overall aerodynamic performance because it shows an average L over D ratio of 3.92, which was greater than the other airfoils analyzed, and a CL max of 0.304. The geometry mapped for this airfoil can be seen on the top, and the results are seen on the bottom of this slide.